All right. Okay, so the first question is, which group is this test biased against? So here's the test score. So this might be a score of a test you might use in hiring firefighters. So that's one that's been in the news lately. So we're going to give a test, map reading, maybe a measure of how well you can drag a 185-pound sack, a number of other driving skills, if you're going to be a person that has to drive the fire truck. Things like that might be in your test. The criterion is how well you do the job. In the case of IQ, what's the test supposed to predict? What's the test designed to do? Predict success in school. Predict which kids are going to fall behind with standard education. So that's the test is the test, and the criterion is what it's supposed to predict. In the case of a pregnancy test, the test down here might be how blue some stick that's dipped into urine turns, and the criterion is what?
Are you pregnant?
The person's actually pregnant, right? A PSA test for you men that have prostate glands. The prostate test is supposed to measure what? Whether or not you have cancer, prostate cancer, and the criterion is, do the people actually have prostate cancer? And that's one of the issues. Is that test at all valid? The guy who invented it, incidentally, has now published an article saying he wished he hadn't invented it. The test is so bad, causing people to get surgeries and all kind of nasty things done to them that might be causing more harm than good, the PSA test. So we have tests and a criterion. It could be a medical test, could be an IQ test, could be a selection test for hiring people, and you have a criterion that it's supposed to predict. Now, a test is reliable. If tested and retest, you get a high correlation. It's valid if the test predicts what it's supposed to predict, but it might also be biased. And so this diagram shows us a case where it might be biased, and in this case the bias is related to some group membership, like maybe gender for firefighting, for hiring firefighters, or maybe in the case of the French schools, it might be, you know, whether the person is Catholic or Protestant. Those of you that aren't aware of it, that in nations that have had where the government tries to take over religion, they've had a large number of religious wars. In Germany, you had the war between the Catholics and Protestants came out even, wiped out about 2/3 of the population in parts of Germany, and 1/3 of the population overall were killed in the religious wars there. France, they had 9 religious wars. The Protestants lost out. The Catholics won there. Germany was a draw. In England, the Protestants won out. Chopped the head off the king. They got rid of the Catholics. The Catholics were suppressed for a while. So different nations, you know, in Northern Ireland, they're still quarreling about it. There's peace there right now, but for hundreds of years, people have been killing each other over religion. So you have group membership might make a difference somehow in how the test predicts a criterion. And the way you decide is you ask for a given test score, is one group doing better than the other group than they're predicted to do based on the test. And in this case, it's biased against A. Even though both groups do equally well on the test, this test is biased against A. Here's one, again, where for the same test score, group A is doing better than B. Here, group A does worse on the test than B, but they do equally well on the criterion, so they can do the job just as well, but the test says they can't. So it's biased against A. So this one, again, is biased against A. Oops, I wrote B in there. This one's biased against A again. Yeah, if you catch me writing the wrong thing, call it out. This one, the prediction is the same between the two groups. For the same test score, you predict, it equally well predicts, even though they don't do as well, equally well on the test. So this one's unbiased. And for this one, it looks like this one is biased against B, because for a given test score, group B does better on the test. How many got that? So in order to answer this question, you don't just look at how they do on the test or how they do on the criterion, but how the relationship between test and criterion differs for the two groups. And if you're doing better, if you can do the job equally well, but the test says you can't, right? Or if you can do the job better than somebody else from the other group with the same test score, it's biased against that group. So doing the job well is the criterion, all right? Okay, any questions about that? So that's the definition of test bias, and it's a little more complicated than you hear in the news. The news will report, they get excited and say a test is biased if there's any group difference. I haven't seen it this semester, but in previous semesters teaching this course, front page of the LA Times, it says, the SAT math is biased against women because women don't do as well on the SAT math, the Scholastic Aptitude Test for math, as men do on average. What's the correlation between gender and SAT math? 0.1. Is that a big correlation? 0.1, square it, 0.01. Would you get excited to go to the mall for 1% of the variance, 1% off today? Not a very big relationship, but it made the front cover of the Times and got people to conclude the test was biased because women are not doing as well. Well, the women are not taking as many math courses in high school either. And for some reason, I don't understand yet, they're not majoring in engineering at the universities like this one. They don't apply to the schools of engineering. That's a mystery yet to be explained. We don't want to just say, well, we don't have to worry about it because the test is biased. You know, the test is biased. Obviously, it's a bias in the test, so forget about it. We don't have a problem. We don't have to think about it. Right? We just blame the test and not have a problem to think about or worry about. There's a question you can ask is, why is it that few women? Are there racial correlates with IQ? Yes. Correlations are about 0.2. 0.2 a big correlation to get excited about? 4% of the variance. Remember I asked you this question? Suppose it said for you today only 4% off. Would you get excited, run to the mall? Not a big deal, but the racists jump on it and say this proves my group is better than your group. And other people say, it proves the test is biased, you have to throw it away. So don't get excited by people that don't, or they think it has something to do with causation. If A and B are correlated, it means that A must cause B or B must cause A, or some factor C must cause both A and B. The right answer is none of the above. There's no causal relationship there. We're talking about small correlations, and it doesn't necessarily mean the test is biased. But if there is a difference, as soon as you say, well, the test is biased so you can forget about it, then you're saying, well, there might be some issue here that should be explored and studied, and yet people are saying, well, just forget about it, we don't need to worry about it. And I was saying it to you at the end last time, we're seeing modern counterparts of that today. There's certain things people don't like to think about, like global warming. Should we really try to reduce the amount of coal and gas and gasoline that's being burnt up? I mean, we know we're producing a lot of carbon dioxide in the atmosphere. Should we be worrying about this? Well, some people are saying, no, we don't even want to talk about it. Don't even want to have those words used. We're going to tell government employees not to use words like global warming. Well, that's not going to solve the problem. It's not going to keep the sea levels from rising. In the state of Florida, they should be worrying about it. They shouldn't be trying to cover it up, pretend that these problems don't exist. All right, so what are the empirical coefficients? Parent-child correlation in IQ is 0.5. The father-son correlation in height is 0.5. That's the same as the mother-daughter correlation, or the father-daughter, or the mother-son correlations. Are all about 0.5. The test-retest correlation for the Stanford-Binet is 0.97. If you use the same form but an alternate form, you can think of that as another way of getting reliability is 0.95. So if you put a number up in that region, that's good enough for us. Since this research was done that I cited to you, people have been working on the Stanford-Binet, trying to improve the items, update things. There was an item on there about what is Mars. It used to be that Mars was an item that kids didn't get right till a later age. Now they're getting it right at an earlier age, as if Mars being in the news is providing more information about it than in the past. So they continue to work on these tests. The validity of the Stanford-Binet is 0.6, whether measured by the correlation. It's supposed to predict validity is, does the test correlate with what it's supposed to? So the test in the case of IQ would be the IQ test. And in the case of the criterion, it's school grades. And it looks something like this for different group memberships, although Asians do a little better on the test than other ethnic groups. So Asian Americans, like Japanese and Chinese Americans, this data is based in California, but they tend to get slightly better grades, as if the test is biased against them a little bit. Other people said, that's not fair, they're doing better in school because they study. But that's what the test is supposed to measure, all right, is success in school. So there's a little bit of evidence for that. There's a lot of theories about test biases. All right, so it's point 6 is the correlation between the IQ test and GPA. So either if you measure GPA as your index of success in school, or if you measure scholastic achievement test. And we discussed the fact that both of these criteria have various problems. GPA may include whether a person's willing to do the work, whether they're well behaved and things like that. The scholastic achievement tests have the problem that they're oftentimes a smaller sample of behavior, just 1 day or 2 days of testing, as opposed to GPA theoretically could be over a whole year of work that a person has done. So both of them are not ideal measures, but both of them come out with similar correlations, validity correlations in the neighborhood of 0.6. Okay, Johnny is 10 years old and his mental age is 8.5. Well, the definition for IQ is 100 times mental age divided by chronological age, where MA is the mental age. His mental age is 8.5 because he does as well as the average 8.5-year-old on the tests. So you just look and ask, how well do 8.5-year-olds do on the test? And that's how Johnny does. So he's like the average 8.5-year-old. So his mental age is 8.5. Chronological age means his clock age, so when was he born? And his chronological age was given as 10 years old, and so that means 85. So his IQ is 85. And we know the distribution of IQ. Here's from one of the editions of Calit. So one of the editions, like intelligence, is in chapter 10. For some of you, for a lot of you, it's in chapter 9 for the editions you're using in this semester. Here's the distribution. He says 96%. He sort of rounded it off. He's rounded off 2.5% in the 2% in the tails. I'm putting 2.5% in the tails. So he puts 96% in here. So I'm like revising that a little bit. If you look at your Z table, it's actually a Z of 1.96 that has exactly 2.5% out there in the tail. So I had to do a little rounding to give you the numbers I gave you. I rounded the 1.96 off to 2, but that's also the numbers I gave you are sort of like the T distribution with 60 degrees of freedom. But anyway, so I had to do a little rounding. He did a little rounding. We have a little bit different rounding, but I'm asking you to go with this. Mean of 100, standard deviation of 15. He has an IQ of 85. So we have 34% here, we've got 13.5% here, we've got 2.5% here. Adding these two together, you get 16%. So the answer here is to A is his IQ is 85, and to B the answer is what percent are 1.5 years below or more? That means they have IQs less than 85. So that means 16%. How many got that? So you had to relate that. All right, so what did you have to do this? The equation for IQ. Questions about how to calculate IQ. You need to know the equation for IQ. Mental age divided by chronological age. Once you get it into an IQ, then you know how to put it on a normal distribution and answer questions now. So you already should know the normal distribution and the landmark normal distribution. You should know that 16% have IQs below 85, and that corresponds to the question, what percent of 10-year-olds are like 8.5 mental age or below? All right, so you need to connect these two ideas, one that we already had with one that we just did last time, all right? Questions about that? Lee says I don't wait long enough for her to ask her question. She takes a while, so I'm waiting.
You're good.
You have a question? You're okay on that one. All right. Anybody else have a question on there? Okay. Piaget. So if you saw the videos and read the book about Piaget, Piaget was a student of Binet. And he got his start asking this kind of question. The kids below a certain age can't copy the square. And then later they can copy the square. What made them go through a transition from not being able to copy the square to copying the square? And he thought of two ideas. It could be biological maturation. So it could be, you know, that as the kids, first they start off, they don't know how to be tall. But as they get older, they eat more food and they learn how to be tall. And then some people don't know how to be bald yet, but they learn as they get older to be bald. And when they get to be about 35, 40, their hair starts falling out. And then when they're 60 or so, they've learned how to be bald. And you're making funny faces because you don't think of that as learning. That's biological maturation. Something's happening biologically. Something's happening biologically. This is maturation. They're growing bigger, right? So is it biological maturation or is it learning? So some changes are happening. It could be the ability to copy the square. Maybe we can teach kids how to copy a square. Give them pencils and papers and take the 3-year-old and have them practice and practice. Can you get them to do it? And Piaget concluded, no, that it's biological maturation. And he had this stage theory of development in which a neuron grows and makes a connection, and all of a sudden now you're in another stage of development. You can answer questions like, if I pour the water from this big jar, which is really big and wide, but the amount of water looks not very tall, into a tall skinny jar, and the water goes up to here, now it looks like more. Is this more or the same or less? Now that and kids below a certain age, when you pour it into the tall skinny jar, they say, oh, there's more water now, and I pour it back, and now it fills up this, and I pour it back again. At some age, they start saying it's the same amount of water, no matter whether you put it in the tall skinny jar, and so they've learned and they've gotten to a new stage of development. Another thing you should have learned from the videos also is that all sorts of people are attacking and disagreeing with Piaget. And we may get to say more about that, but the answer is, can you increase the mental age by learning? And his answer was no. But he cites in one of the videos that he showed a kid this, and I want you to draw this, and the kid just couldn't produce the lines. Tried to get him to do it, they couldn't do it. Just sent the kid home for a few weeks, brought him back, and said, remember I showed you something to draw? And the kid went, yeah. And he immediately drew the same thing. So he just got 6 months older, now he could draw, he remembered it even. He could draw what it was that he couldn't do at an earlier age. According to Piaget, that was biological maturation. So you should know this classic theory, a stage theory of developmental psych. I'm going to skip over that. We may come back to it a little bit more after the break. And if you haven't viewed the videos in development and read the chapter yet, go ahead and do that. Well, the correlation between IQ test at age 6 and adult is 0.6, so we've been doing problems like this. I'm going to erase the material up here if it's okay. Any final questions about this? Going twice? 3 times? Okay. All right. So, here's the equation that we need. We need the prediction equation. So the problem is the IQ is 70 at age 6. So we're going to assume that the mean of x is equal to y is equal to 100. That the standard deviation of x is equal to standard deviation of y is equal to 15. That it's a bivariate normal distribution. These are all the standard assumptions. And that the correlation coefficient is equal to 0.6. So these are the things we get to do when we have an IQ problem like this. And we're looking at the correlation in IQ between IQ at age 6. So here's the IQ test given at age 6. Here's the IQ test given as an adult. Each point represents a child. So we've got a whole lot of children here. the mean IQ is 100 at age 6, and the mean IQ is 100 as an adult, and the correlation is 0.6, and you should, well, I should lower this correlation a little bit by adding 2 more points, but a correlation of 0.6 is a correlation of 0.6. It's not a perfect correlation, but it's 0.6 correlation. Now we have a child whose IQ is 70. We need to predict the value as an adult. So the equation is z hat yi is equal to rxy z sub x sub I. So here's our prediction equation. And we can substitute everything in. We have y hat I minus 100 divided by 15 is equal to 0.6 times the child's IQ. So Jane has an IQ of 70 at age 6. So we're going to put 70 in here, 115. So I just substituted in. Any questions about setting the problem up? So you need to know the prediction equation, which is very simple. The z-score of the prediction is just the correlation coefficient times the z-score of the predictor. Remember, this correlation has to be between 0 and 1, so it means that the z-score of the prediction is always going to be less extreme. That means it has regression to the mean. If the correlation is 0, you're going to end up just, the predicted z-score will be 0, you just should predict the mean. So if x is uncorrelated with y, just predict the mean of y. The higher the correlation, when it's positive and high, then the z-score might be as high as the z-score of prediction, as high as the z-score of the predictor, but never that extreme. So we can multiply both sides by 15. We have a negative 30 times 6 times 30 is going to be negative 18. Add 100 to both sides and we get y hat I is equal to 82. How many got that? Okay, so it looks like most people now. Questions about that? How to do that? You need the prediction equation, and they basically substitute these things in here. So this is just like problem number 17. If you haven't done 17, then by all means do it. Maybe this explained it to you. Do homework problem number 17 that's listed there in the Titanium. All right, that's A. She was 70, and we're predicting she's going to go up in IQ. So here she was at 70. Here's the predicted value, not as low as 70. So here's the identity line. Here's what it would be if it's 70. We're predicting she's going to go up to 82. And as Lee was pointing out last time, not every child is going to go up to 82. That's the average of the children like this. The average of the children whose IQs at age 6 are 70, is going to be 82. So they're going to go up 12 points on the average. If I had a program that took kids at age 70 and caused them to increase in IQ by 5 points, would that be a good program? No, because you expect them to go up by 12 points. How should you test such a program? Have a control group. Take kids of 70 and randomly assign them to two conditions, one experimental group, one control group, and compare the two groups. That's the best way to do it. How can you cheat people out of their money? And I'm not recommending you do this, but I want you to recognize it so you won't be cheated. I mean, the book How to Lie with Statistics is not a book of advice of what you should do, but a book of how to be warned against what people might do when tricking you. If somebody says, I will give you, your child has a low IQ, I will increase their IQ by 5 points. Just give me $10,000 a year for, between the age of 6 and 16 when they're an adult, 10 years, $10,000 a year, $100,000. I will guarantee that their IQ will increase by 5 points or your money back. Is that a good deal? It might sound like it if you hadn't had intro psych, because you know it should go up by 12 points. This is a cheat. And most kids are going to go up by at least that much. The average kid is going to go up by 12 points. How many kids are going to go down? Now notice here's the distribution of the children, of these children's IQs. Some of them are going up. The ones down here have actually gone down. And so that was what question B was, what is the probability that she's actually going to decrease? And to answer that, you need the variance of the residuals, which is s squared y minus y hat is equal to 1 minus r squared xy s squared y. So this was the third of the three formulas that I wanted you to memorize on page 7 of the handout. This is the variance of the residual. And 1 minus r squared is 1 minus 0.6 squared times 225 is the variance, because if the standard deviation was 15, the variance is 225. So this is equal to 0.64 times 225 is 144. So that means that the standard deviation of these children's IQs is going to be 12. So that mean is going to be 82, standard deviation 12. So let's draw that distribution and answer the question. Here's our standard normal distribution that we have memorized. 1, 2, negative 1, negative 2, 0.025, 0.135, 0.34, 0.34, 0.135, 0.025. We now know that the mean is going to be 82. We worked that out right here. The predicted value is also the same as the mean value of y given x. And the standard deviation is now 12. So once we know the value of x, the standard deviation has gone down from 15 to 12. So the 0.6 correlation reduced the variance left over. Didn't reduce it by a whole lot, it reduced it by 36%. That means we still had to pay $64. That means if we were buying a suit at the mall for $225, or a purse, I never know what purses should cost, right? Clint Eastwood's daughter burnt up a purse worth $100,000 as a kind of an art project. She wanted people to feel something. What do you folks feel when you hear she burnt up a $100,000 purse? You know, I didn't even know a purse should cost $100,000. But then other people said, some people were annoyed. Some people said, she got it on sale for $80,000, so it wasn't a big deal. Burn that up. That's what happens when you cut the taxes for millionaires. They burn up $100,000 purses. And I don't know why. I mean, this wasn't even a jeweled purse, but just a purse. Anyhow, so let's say you're going to buy a purse for $225. You get 36% off. It still costs 64%. It means it's going to cost you $144. We take the square root of that, we get to 12. So we can add 12 to that, plus 12, brings us to 94. Add another 12, we get to 106. So the odds she's going to end up with an IQ above 106 is 2.5%. Subtract 12, we get down to 70. Well, that's where she was. So the odds are, all this area, this is the probability she's going to increase. 0.5, these three, plus 0.34, so that's 84%. She's got a probability of 0.84, or 84% of the kids are going to increase in IQ, not all of them. And 16% are going to end up with lower IQs than 70. And so the answer to the question was, what's the probability she's actually going to decrease is 16%. Because 16, she was 70, and this is the probability of ending up with an IQ less than 70. Right? So here's how we use that, and that was the question that Lee was asking by saying, not every kid, when you make these correlations, not every kid is going to go up whose IQ is 70 at 6, but most of them are. So if your child has an IQ of 70 at age 6, I wouldn't say, oh, that's about the end of that, you know, reserve them a place in a mental institution. Or if they're 130, the odds are they're going to drop. I wouldn't necessarily reserve a place at Harvard either. All right. My daughter was off the charts in height and weight. She was more than 3 standard deviations below the mean. She was really tiny. So compared to the other kids in school, you know, they were this tall and she was like this. More than 3 standard deviations, way off the charts. They said she was going to be really tiny. Maybe we should get her in gymnastics, stuff like that. They were testing her for multiple sclerosis and muscular dystrophy and all these strange diseases. And then at some point, she went past her friends and ended up 5'6". Just pretty much close to the average. So all kind of things are going to happen. There's a lot of variance left over here, and this is the point Lee was trying to bring out last time. And also how to address it statistically to try to get a balanced presentation of it. All right. Any questions about that problem right there? So there we used all the tricks that were on that page 7 of that handout right there. Okay, you can restart that.